Okay. Welcome everybody to our conference, Happy and Healthy Living on Mars. My name is Annemiek Bosch. I'm the president of the Mars Society Netherlands.
And I'm Tijn Vennersand, and I'm the vice president. And I'm just wondering and hoping whether we can have a very enjoyable evening with a lot of interesting guests and speakers. We still have little difficulties with Mr. Zubrin to get him online. So I'm wondering whether we can just start with maybe first presenter and introduce us, and then hopefully we get Mr. Zubrin online a bit later.
Yes. First, I would like to say we attracted some very excellent speakers who will be talking about the theme Happy and Healthy Living on Mars from different perspectives. So we have history, design, technology, science. If you have any questions for our speakers, you can ask them in the chat and we will make a selection of those. So because we're still waiting for Dr. Zubrin, I'd like to start with the first speaker. This is Mr. Lucas Figlietti. Mr. Figlietti is an airline pilot who had the chance in this job to meet with the people who joined the Apollo program. And he is author of the book Apollo Confidential, which contains the biographies of all the moonwalkers. So in his lecture, he will draw lessons from the past for the well-being of people in space. Lucas, welcome.
Thank you very much. Welcome to everybody. And today I took my favorite t-shirt, of course, to be with you. That's very important. And let me try to start with my presentation now. So, actually, the title is Lesson from the Moon for Survival, and I took a beautiful picture. For me, the most iconic picture, I would say, for the Apollo program, because you see the last man on the moon. This is Captain Gene Cernan on the inside his Lunar Module, and it was the very last few moments on the lunar surface in December 1972. And for me, important is to see at his face, you can recognize all kind of emotion. He was exhausted, he's happy, he's relieved, maybe some worry because they have to prepare the takeoff to come back to Earth. And also interesting is to see a true explorer on the moon with his face, with his underwear full of lunar dust. I love that picture, and I want to speak more about the lesson from the moon for survival. Actually, if we look a little bit back, it was always a desire, a profound desire of humanity to explore, to go further and further, and to discover new worlds, new territories. And for me, it's interesting to see that in history of mankind, during not decades, not centuries, during 1,000 of years, man stayed on his Earth, on his planet, and it was quite a journey to discover all the places where he lived in the Earth. And it was, of course, quite difficult sometimes because you have to cross ocean to go to different region, hostile region, but it was still on Earth. It was still with environment, with oxygen, with some fresh air to breathe, with some food around, some water around to survive. And things change when man decided to leave his cradle and to go even farther, to discover the outer space. Started in 1961 with Yuri Gagarin, until now almost 600 people left Earth to go in outer space, and most of them stayed on the Earth low orbit, and only 24 of them went 1,000 times farther and to discover a new world, the moon. But now we stay a little bit with that image and to consider the problems linked for a survival and in outer space. Because when you see that picture, I would like to emphasize about three important problems you have when you make exploration outside Earth. First is a vacuum, is the blackness of space, is an hostile place with a huge difference of temperatures also. And you have the problem of radiation, the cosmic radiation, but also the solar radiation from our star, the sun, and also the problematic of meteorites or all kind of object traveling into space. And this, I would like to go more into detail and to show you that pictures. And this is important to understand that one also of the big problem is when you travel in outer space, as I said before, you have radiation, cosmic radiation, and also solar radiation. And this is, I would like to explain you a little bit the story behind the discovery of that phenomena. Actually, it was a long time ago, and people on Earth were very amazed to see on the polar area on the Earth these beautiful lights in the sky called Aurora Borealis. And scientists discovered that, in fact, this was some elements coming from outer space and coming into our atmosphere, captured by the magnetosphere on the Earth and making these beautiful lights. But that was also the evidence that something is outside in the outer space, is not a pure vacuum, it's some other elements. And this was a few professors and scientists studying these cosmic rays. And also I would like, one of them was Swiss Professor Oechsler, and Oechsler in the 50s wrote a paper and with the idea that maybe the Earth should be had a kind of protection, a kind of belt around it. But it was only less than a decade later, than actually on January 31, 1958, with Explorer 1, that we finally made the measurement and confirmed that theory. And the name of this belt has been named not from people who had the theory behind, but from the professor who actually makes the measures prove it. It was Professor Van Belt. So is a Van Allen belt, sorry. And this is a story just to explain to you, and like a few of the scientists told me who worked during the 50s, that it was time when actually people couldn't go to space, but it was space who came to the people on Earth through meteorites also. And I will come to the next also consideration with solar wind and with the cosmic radiation in general, because there's a lot of assumption that flying outside the Van Allen belt, you could have a severe damage or even die. It's not possible to survive. and that's fortunately not correct. And if you can see correctly in my illustration, you see that the moon is actually most of the time outside that shield, exposed to the solar flares. And that's why during the Apollo programs, it was consideration how to protect the crew, because if the crew were exposed to the solar flares, it could have been very dangerous, lethal, not dying maybe within minutes, but maybe within the next few years. And it was a concern, but I will explain later on how they did that. And so a new science came. It was the space weather forecast, because it was important. If you send people outside that belt, you want them to be protected. And so it was observation from Earth to see. Fortunately, we knew that the solar flares were in a kind of cycles, every same period of years coming in. And with big telescopes, it was also possible to look at the sun and to predict sometimes if we were in the vicinity of that situation. And but the problem is, if solar eruptions is coming, you don't have even 8 minutes to protect yourself. So it was really very important also for Apollo program to make that weather forecast. And then the other problem is the meteorites. A meteorite, when you see the surface of the moon, you can recognize it's a lot of impacts, and that was a consideration. How high is the risk to have such collision also on outer space, on the lunar surface? And I remember my friend Jack Schmidt, Apollo 17 astronauts, who told that he saw himself a few times meteorites entering the atmosphere around the Earth, but also hitting the surface on the moon. So it was really a consideration. So now I will say, let's go to the moon. And interesting numbers. It's funny with numbers, because sometimes, of course, you can discover very interesting facts. The distance between Earth and the moon is approximately 360,000 kilometers. And as I told you before, is out of 580 persons who flew into space, only 24 left low Earth orbit, which is, we said below, we'll say 364 kilometers to stay with that same number. So going to the moon is 1,000 times farther than the most majority of astronauts and cosmonauts, taikonauts who went to outer space. And if you want to go to Mars, it's again the same factor of 1,000, because now it's 364 million kilometers. That's a funny fact. Out of the 24 Lunar Explorers who went to the moon between December 1968 and December 1972, within 4 years, we see all the crews. If you can look at this guy, you see, whoa, but actually, Lucas, they are 27, not 24, if I counted correctly. Yes, but 3 of them flew twice to the moon, and that's just amazing. And you see it was John Young, who flew on 10 and 16. You have Gene Cernan on 10 also, and then he flew on 17, and Jim Lovell on 8 and 13. So there are, out of the 580 person who flew into space, the 24 only person who left low Earth orbit to discover another place. And they went to on the moon, and of course the first mission the most important consideration was to survive that flight. And if you want to survive that flight to make the first landing on the moon, you have to choose a very flat area. And also from the celestial orbit, it's very important to have them all align approximately on the equator of the lunar surface. And that's why if you see Apollo 11, 12, and 14, the first three landings, it was approximately on that line. Interesting enough, if you compare the moon and Europe, you can see the distances. The moon, the diameter of the moon is something like between Lisbon, Portugal, and Moscow in Russia. And it was you have a more understanding of the distances. It was a quite interesting to see the last mission also went more to the north, to the south, more dangerous area with mountains, with difficult to land. And this made also very dangerous but interesting experience. When they went on the moon, on that very hostile environment, to survive as long as they stayed on their lunar module, that was I will say quite comfortable for back in the time we can consider. And they had everything in to survive. They had, if you see the food and beverage, they had fuel cells to give them some fresh water. With that fresh water, they had hydrated some food they could eat. It was a lot, actually. When I discovered that, I was also quite surprised, because if you see that 9 different drinks, and if you see all the kind of breakfast, candy, desserts, so sandwiches, meats, it made quite a lot of diversity on the food they had for that first journey out in outer space to go to another heavenly body, the moon. And you have a few examples here. And also for personal care, that was maybe the most difficult part of the journey, is just to keep everything clean. And they had a very, as you can see, primitive facilities, I will say, but everything worked quite well. And of course, if you want to survive, then for longer mission and to go to Mars, you need another kind of technology, of course. To sleep on the moon, it was interesting to know. I don't know if people are very aware, because the first mission, Apollo 11, they stayed just a few hours, but later on, starting with Apollo 12, that stayed 2 days, and starting with Apollo 15, even 3 days on the lunar surface. So they had to sleep, and to sleep, they had an hammock, you can see on the right-hand side, with a commander above, and below the commander, it was the Lunar Module pilots. You can see on that pictures, and there are a few interesting story about that, because when you consider that you have only 1/6 G, so the pressure on your shoulder, on your body, is not 0 G, of course. You have a little sense of gravity, but the problem is you don't feel comfortable. And the first crew from 11, 12, 14 who had to stay on the moon, it was really not easy to fall asleep, for different reasons also. The first remission, they told the crew, stay into your spacesuit. And the problem with the spacesuit was the ring around the neck, because the metal ring, when you're laying down on the hammock, it hurt a lot of your neck. And I remember my friend Edgar Mitchell, Apollo 14, told me it was almost impossible to sleep. It hurt. It was not very comfortable. And if I see at the picture, have a small story interesting, because if you look carefully on the Lunar Module interest of Apollo 14, you see that the right-hand side feet on the Lunar Module is quite in a small crater. You see some thing, because the Lunar Module has moved during the night, and during that movement, only for a few centimeters, but big enough to have waken up, and the crew were very, very anxious, because they thought, oh, we are tipping over, it's over. We are staying on the lunar surface forever. And they were quite shocked. And another problem to sleeping on the moon back on these days was that the skin of the lunar module was so thin. You can imagine aluminum, but from Red Bull, from Coca-Cola. If you see that that aluminum bug in your hand, you can squeeze really easily, and the skin of the lunar module went even thinner than this aluminum can. So when the inside of the lunar module had to be pressurized, it was a lot of noise, and it was quite also alarming for the crew. It was difficult for them. But if you go outside Lunar Module, you have another problem. You have to have another spacecraft called the spacesuit. And that was also very difficult to develop this spacesuit. And the first who tried that kind of spacesuit was the gentleman in the middle of the picture called Wile Post. It was in 1934. And he made a record. He flew at 40,000 feet, wearing that very first space suit. And the Apollo space suit that we all know, we can see on that picture, developed for Apollo program, where the most, I will say, it was so genius. It was extremely interesting from the technical side to see that, for example, they had 21 layers of different materials. You can read yourself, but something I would like to emphasize and to correct, because a lot of people are mixing it. Actually, if you see Teflon used during Apollo program has been invented before the Second World War in 1938. Nothing to do with a spin-up invention for Apollo program. They were other materials. They were other technology invented for Apollo program, but not Teflon, as we heard too much. And with the spacesuit, when they come outside, the biggest problem, and also Charlie Duke, Moonwalker Apollo 16, we spoke a lot about that, because this is Charlie on the surface on the moon at Shadow Rock. You can see on that picture. You cannot recognize a white spacesuit anymore, because that picture has been taken 3 days. The third day on the lunar surface, and you see it's gray, full of moon dust. And the moon dust is very dangerous. Why? Because it's tiny particles, and is with cutting edge. It cut everything, because on the lunar surface you don't have wind, you don't have water to make that element coming more rounded, like rocks inside a bedrock, for example. So it's small razors and cutting everything. And after this Thursday on the lunar surface, they had problems with the zipper. They had some problems because lunar dust was really aggressive. I love that picture too, because it's not the right colors, but if you see on the right side, just above his hand, his right hand, you can see something shiny. This is actually some crystals. And Charlie told me it was beautiful blue crystals. Can you imagine? It's just amazing. It's amazing, at least. And having this space in lunar surface, you have to learn how to survive, and to learn how to move on the moon. It wasn't easy, and this is a proof with some pictures showing them struggling with their spacesuit.
Take me on a trip, I'd like to go someday. Take me to New York, I'd love to see LA. I really want to come kick it with you. You'll be my American boy, American boy. Hey sister, it's really nice to meet ya. I just met this 5'7" guy who's just my type.
Beautiful, beautiful footages. I cannot barely believe that these pictures more than 50 years old. It's just amazing. And now at the end of my presentation, I come back with that picture, and I will say that thanks to the Apollo program, humanity learned to go and explore a new world. They are truly the successor, the dying successors of Christopher Columbus, because they discover a new world. And now it's time to go even further, to go to Mars. Because once you and me, we are going to Mars, we can enjoy beautiful sunset like this one. Thank you very much for your attention.
Thank you, Lucas. That was very interesting. I just heard a rumor about the first step on the moon by Armstrong, that it wasn't actually his first step because they wanted to test whether he would fall in the moon dust. Is that true?
No, because actually when Neil Armstrong went down, it was filmed. It was a live TV broadcast from an automatic camera was placed on the side on the descent stage of the Lunar Module. So it was everything live. I have to say, not exactly live, because images has to go first to Australia, for Australia to be recorded and to be broadcasted again to the United States, and from the United States to be broadcasted around the world. But my knowledge of that, I will say no, is that really is live images you can see.
Okay, thank you. You have a question for him, Tai?
Yeah, there was a question about whether the moon dust is as sharp or similar to Martian dust, and can we then also practice on the moon to make certain that people will be safe on Mars?
That's a good question, and to be frank with you, I don't know about Mars dust. So I don't want to answer that, but of course it was a great lesson from the moon, knowing that this could be a great problem, and that's so important now to take some Mars dust back to Earth and to see exactly what is the composition, what is the characteristic, because it could be a problem also on Mars, I can imagine.
Annemiek, can I answer that question? Wiege Wamelink, working on Mars
Sure.
and moon soil simulant. I will be presenting later, but I've worked with both simulants, and there's a big difference between Mars soil and moon soil, because moon soil is just rock that has decayed due to radiation, and there is no weathering on the moon, so it stays sharp, exactly as you said, Lucas. But on Mars, of course, that's different, because in the past we had water there, so there was a effect of water, so weathering already, and we still have Martian dust storms that would make the particles less sharp. So that's a big difference, I think, between both soils. Still, those soils also present their own problems. Thank you.
Thank you.
Okay, thank you for that answer, Wieger, and thank you for your lecture, Lucas. It was very interesting.
Thank you very much.
And okay, so our next speaker is actually Dr. Wieger Wameling from Wageningen University. He is leading the project Food for Mars and Moon, and he'll be talking about how food can be both beneficial for the health and the happiness of people on Mars. So welcome, Wieger.
Thank you. And I also put on a special t-shirt, but in our case, it's our own project t-shirt, which is for sale, by the way. So I've said that already, and I'm going to share my presentation. Yes, and then start. Yeah. Okay, thank you. And thank you for having this opportunity for me to talk about our project. It's going on from 2013, trying to grow crops on Mars and Moon. Well, not actually there, as you may imagine, but at least in Wageningen in the Netherlands. First, a bit about the problems we face. And the first one is, of course, the gravity that is much lower than it is on Earth, about 1/3. And to start with a rather problematic thing, we cannot change gravity on Earth. So it's very difficult to do experiments under that gravity that is present at Mars, and growing crops, well, it may be influenced by that lower gravity. Of course, we know that plants grow on the ISS with microgravity, so I don't imagine that there will be major problems, but, well, it's still different. And, well, if you do science, of course, you have to test it. Very difficult for me as well on the surface of Mars is that there's almost no air, not enough for plants to grow in, at least. What is very neat and different from the Moon, of course, is that a day lasts about 24 hours and 36 minutes, so almost the same as on Earth. I don't think that will be a problem for plants. It may be for people, but, well, I don't do people. There's lots of ice on Mars, which is very beneficial for plant growth, of course, although plants need liquid water, and as far as we know, there's still no liquid water at the surface of Mars, at least not at the moment. And that alone already could cause a major problem. And it's normally very cold on Mars. -60, -80 is quite normal. Don't know why that's happening. But at least there is ice, and you can melt it, of course, and then you have water. And we already discussed a bit. There is soil. Well, I couldn't call it soil. I should say regolith. But at least we can maybe use it to grow plants in. And that's what we want to do. So that people who go to Mars, and also to the Moon, by the way, have their own fresh food. Well, and already mentioned also by Lucas is that radiation is a problem, because Mars does not have a magnetic shield, not a magnetic field. So that means that cosmic radiation, including that from the sun, just arrives on the surface of Mars. And that could be problematic for humans to live there, but maybe also for plants. And I'll get back to that later on. Well, we can protect ourselves. You could go live in caves, but there's also another solution. And then we can go to this picture, and that is that we go below ground, and that we make a kind of dome, a bunker if you want to, and we can live in there, protected from cosmic radiation, and with a layer of soil on top of it, so that we are really protected. And well, for humans, that may not be the most ideal circumstances to live in. It's difficult to go outside, outdoors, and yeah, even if you go outdoors, you have to suit up. You never can go outdoors without a suit, so you're always kind of indoors. But hopefully, if we have nice things to eat, it will cheer up the people when they are there. And for me, this concept is quite easy because what we do is take the regolith outside and we take the ice, bring it indoors and use it to grow crops in. And since I do it indoors, I have the rest of the circumstances all controlled because I can have normal air where humans also can breathe. And I use LED lights, LED lights to grow the crops in, which I can manipulate. And of course, the same air pressure. So I use the ice and the soil from outdoors. And for the rest, I bring some stuff from Earth. And that's in the next picture. This is what we're basically working on. So we're not only working on just growing crops, as you see here, a pea, because that's not enough. And you can bring the seeds, maybe you can get the soil working, the regolith, and you can grow your crops indoors and have some fresh food instead of the food we saw earlier. Um, but that's not enough because then you would have had one cycle and you would have to bring in seeds every time. So that's not very economical. And the thing what we want to do is in the end to set up a sustainable agricultural ecosystem for Mars so that you only have to bring some things at your first trip and then you can start your own ecosystem over there, indoors, of course. And these are the things we think are needed. Well, of course, the seeds for the crops to grow, but they need to be pollinated by insects or by wind. Wind we can make, but pollination, we've done it by hand in our experiments, but that's very complicated and laborious. You could do it by drones, but it's also quite complicated. The easiest way to do that is to bring pollinators, like bumblebees, for instance. And of course, you can bring bumblebees to Mars, even if the trip takes 6 months or 9 months, you can keep them in hibernation and wake them up when you need them on Mars. So only bring the queens. Now, then we go below ground. I need several other organisms. First start with the bacteria. I need bacteria to break down organic matter. So everything that's left over that you don't eat from the crops you've grown. So that can be roots, that can be leaves. And in the case of the peas, we only eat the peas itself, of course. So the rest is organic matter and has to be brought back into the soil. It has to be recycled. Well, bacteria can break down organic matter, so we want to bring them. But of course, you only want to bring bacteria that are beneficial for your plant growth. You don't want to bring bacteria that can carry diseases. So you have to be very careful. You have to pick them species by species. There's another role for bacteria as well, and you can see that under the magnifying glass with the root, that is that bacteria, special bacteria, rhizobium bacteria, can take N2 out of the air and turn that in the end into nitrate. And they share that with the plants. And all legumes, as the pea, can do that. And those rhizobium bacteria could help to fertilize the soil because the soils, well, regolith on Mars contains most of the nutrients that plants need, but nitrate and ammonium, very important for plant growth, are almost absent. And by taking N2 from the air, the normal air we have in the dome where we can breathe, but the plants can live in as well, they can take the N2 out of it and turn it into nitrate and thus help feeding the plant. Now I want to go to fungi and bring fungi as well, especially in the first stages when we're developing this system. I think they will be very important because what the fungi do is that they also live together with the roots of the plants in symbiosis, and that they, with their very dense system of, well, let's say roots, can penetrate the soil and acquire much better than plant roots can nutrients from the soil. And especially in the first stages, in the first years, that will be necessary because it will be, as far as we know at the moment, a poor soil. And then fungi can help to acquire minerals and nutrients for the plant. They share it with the plant via the roots, and the plants share then carbohydrates with the fungi, so they both benefit. Now, to my favorites, that are the worms, earthworms. They have to be brought to Mars because they form an essential part in our system. They can eat the organic matter, they bring it into the soil, and their poo can be manure for the plants. So that's one reason to bring them. Another reason is that they dig burrows, as you can see here as well. So that helps to aerate the soil. Roots of plants need oxygen to function, and this is a way to get the oxygen easier to penetrate the soil. And when we did our first experiments, we also learned that the soils, the regolith, are quite hydrophobic. And so if you add water to it, it just stands on top of it. And if you have worms digging burrows, then it's much easier to water the plants. Now, let's not forget about the humans, because I need them as well, although they are the most difficult part. But I need them to eat my crops and to enjoy it. And what I'm very interested in is the feces of the astronauts, because I want to use that as manure as well. And that's not only the poo, but also the pee, because in principle, that's of course very good manure. And that more or less closes the cycle. And that is what we are working on in Wageningen to accomplish, to get that working, that system. Now, first, experiments on Martian soil. How are we going to do that? Well, there is of course still no real Martian regolith on Earth. And what we do is we use the artificial regoliths that first were made by NASA, but now also by, for instance, University of Central Florida. We have several generations of Mars soil simulants, and that's what we use to do our experiments on. Of course, I would love to do the experiments on the real thing, but well, I think I have to wait another 10 years. So that is what we use. And this is a bit how it looks like. It was our first experiment where we tested 14 different plant species on both Moon and Mars soil simulant, and we had an Earth control. And we had in total 840 pots. As you can see here, 20 replicas of each one, in total 4,200 seeds. And why so many? Because we did analysis on the simulants, and we saw that there are very difficult soils for plants because, well, nitrate is almost lacking, so that's already a problem for plant growth. There are heavy metals in the soil, hydrophobic, and as an extra, the moon soil simulant, I must say, as well, is very sharp. So it can actually penetrate roots and puncture them, and we've seen that also on moon soil simulant. So many seeds, and we thought maybe some will germinate. Well, were we in for a big surprise, because all 14 different species we tried, crop species, and also wild plants, they germinated. Not all seeds germinated, but quite a lot of seeds germinated. So in a way, it was a big success, but also an awful lot of work. But happily, we had some help, and we stick to that, and we followed the experiment for the whole period. But it was a lot of work. And in the end, and that was beyond what we ever expected, we had already flowering plants in our first experiment on Mars soil simulant. And here you see one. This is garden cress, so something you could eat. And this is also the reason why we're looking at a closed agricultural system at the moment, because we already learned in that first experiment that the plants need to be pollinated. And we were in a luxurious greenhouse in Wageningen. And of course, there are no pollinators inside. And if there are any insects inside, then they are immediately killed because they can influence all kinds of experiments. But we needed them for pollination. So we did that by hand. But of course, that is not possible when you're on Mars. Then we went to growing crops. And you see here an example on Mars soil simulant, and you see that all the 10 different crops you can see here are actually germinating and growing. And we didn't include only crops that you really can eat, but also some, well, you can eat them all, of course, but also, for instance, leek and chives, not only because they can nourish you, but also they give taste so that you can actually have a nice, decent meal with lots of flavors. So you can actually enjoy your meal. And of course, you can understand if you have a nice meal, then you're a lot happier than you have to eat astronaut food. So this went already quite well in our second experiment. And the big difference was that we added some organic matter, the harvest of our first experiment, in this soil, and that helps to grow the plants a lot because you get nutrients. The water holding capacity is a lot better because organic matter can hold water and release it slowly. And also it improved general soil conditions. And after a while, we could harvest radishes. This is actually on moon soil simulant, but also on Mars soil simulant. And we had our first red tomatoes on Mars soil simulant, not on moon soil simulant, by the way. And well, of course, you want to taste it, but we didn't do that, not at this stage. By the way, the tomato was not very big. It's about a 5 euro coin size, so they're still quite small. But we optimized that in later experiments, but we didn't taste them yet. I wanted to, of course, but we were not sure it was safe to taste them because we knew there were heavy metals in the soil like zinc, cadmium, lead, and we had to make sure that it was safe to eat them. And not that the lead or the zinc ended up in the fruit. And then go to one of our favorites in a next stage experiment with big buckets, as you can see here. We had potatoes, and I think one of the crops for Mars will be the potato. Not because I'm Dutch and we eat a lot of potatoes, but because you can harvest them very quickly. It took us 2.5 months in the greenhouse to go from potato to harvest, and I think we can even improve that. So maybe go back to 2 months. That means even on Earth you can already have 6 harvests in 1 year. And they don't need much space. The soil simulant is quite good. It's for growing potatoes because it's a kind of sandy-like soil. Potatoes like that, and the potatoes don't need much space. And that's of course very handy when you're in a dome and space in itself in there is limited. Then you want to have your optimal crop growth. And that's also one of the problems I have with many experiments. Also that the ones on ISS, they always grow lettuce, and I can understand that. And well, lettuce like crops because it's easy, it goes quickly. I do it myself as well because I work also with garden cress. Same thing, grows very fast, but it's not something where you can live on. And I think the potato will be one of the key crops. And well, if you have potatoes, then you also want some oil maybe. And we've tried already oily crops. Sorry, I lost the name. Peanuts, of course, and not in itself because they are healthy and they can be very useful for your diet. But of course, you can take oil out of it and then you can make your own French fries, of course, in oil. And that also could make you much more happy when you can, well, maybe once a week have French fries on Mars. Well, and then, of course, it was time to do the first tasting. We invited a TV personality from the Netherlands who does stunts. So we thought, well, maybe that's a good idea to have her taste the first radish. It was very spicy, by the way, the radish. And she tasted it in front of the TV cameras. And I told her, you can eat it, no problem. You try, but you have to clean it because we know the soil contains a lot of heavy metals. So be careful, clean it carefully. You can see the bucket where the water is in. But since it was very spicy, the first thing she did after she had it, she drank from the bucket with the soil simulant, Mars soil simulant, with the heavy metals in. So she did something I told her not to do. But I can assure you she's still alive. So she survived. And of course, we did a lot of control on what was in our crops. Here an example for the tomatoes. And we compared it with earth soil, where we grow the potatoes on earth soil, on moon soil simulant, and of course on Mars soil simulant. And you can see, well, there is of course some iron in it, also some cadmium, chrome, and lead, but the contents are very low and they're way below what is officially allowed. So it's perfectly safe to eat them. And of course, from chrome, you also need to have something in your food because you, in small amounts, you need it to function properly. So we were sure it was safe to eat it and that in principle, at least these simulants can be used for growing crops. Well, and then it was time to have a decent meal. And you can see it here. This was based on the 10 different crops we grew in a very big experiment. We had green beans, for instance. You can see them on the left bottom corner in the main course, which consisted of all 10 different crops. You can see mashed potatoes. You can see the carrots, the peas, the radish, but it and the rucola as well for taste. But it tasted very good. It was like you were eating in a Michelin star restaurant. It was that good. And on the right-hand side, you see potato soup with a bread made of rye and foam made of radish. And that all was made by students from a Wageningen school. And we had a very, very good meal. But maybe you noticed you don't see any meat, and that is why. That is because we think that at least at first you will be vegetarian on Mars, because it costs a lot of space to have any animal on Mars. You could think of insects, but we think you will be vegetarian at least for the first years on Mars. And imagine it would be very difficult to travel in a spaceship with, for instance, a cow or pigs. And there's another reason not to do that because they need quite a lot of food for every kilogram of meat they can produce. So it's very inefficient as well. But still, you can have a very, very nice and decent meal. I think it was one of the best meals I ever had. And that makes you, of course, happy. Now, I told you the worms. I would like to bring the worms, and we did so already some experiments in the simulant. And you can see here a little movie is made by an artist, Wim van Egmond. And on the left-hand side, there are no worms. On the right-hand side, you see the worms in the soil, and you see on top garden cress germinating and growing roots. And you can see that the worms are actually doing their job. They're digging burrows, they go up, they try to find some organic matter and bring it back into the soil. And as you can imagine, this is of course accelerated But in principle, this works, and they can live in these, at least in these simulants. And we did some extensive experiments already with the worms because they are that important for our ecosystem that we want to build. And in one of the experiments, we also had young worms. So we know they can even have offspring in these soils. So in principle, this should work. And this is how we work on all different parts of the ecosystem we want to build. But this is one of the examples. Now, I talked about not bringing animals, but maybe we could bring chickens. And there are several reasons for that. Of course, you can eat the eggs, and that would be a very good addition to your diet, especially since you're vegetarian. You could eat, in the end, the chickens as well, but I don't know if you're willing to do so when you are on Mars and they accompanied you for, well, a couple of years at least. But there's another reason to bring chickens is that they actually are pets. So they can sit on your lap and they can act as pets. So they can be useful, they can lay eggs, but they also can be pets. And well, it may be a little bit funny, but actually that could be very beneficial because imagine you're on Mars. First, you are 6 months in a rocket with a group of people. You cannot escape it, so it's more or less Big Brother, but then in a rocket. And then you go to Mars and you live in your dome, also not very big. And then, of course, it can be very good for general well behaving that you have some pets that can give some comfort when you have difficult times or you have a row with some of your future Martians. So there's more to it than just the eggs to bringing chickens. And then to my last part, I also talked about the radiation, and Lucas did also, that on Mars the radiation is present on the surface. That's a problem for humans, but it may also be a problem for plants. And we tested that. You could imagine that you have a kind of glass dome, although we don't know at the moment how to build one. But imagine that you could use direct sunlight. That would be beneficial. But you would also receive the cosmic radiation. And the big question is, can plants survive that? Well, together with the University of Delft, a student of mine in Katak, she's on the left here, did an experiment. She radiated rye and garden cress with the same amount of radiation that you would receive on the surface on Mars. And what came out is what you see here, is that you see damage on the plants. You see brown parts, we've seen curly plants, we've seen draft growth, and also real black necrosis on the plants. So also the plants are affected by that dosage that Mars gets on radiation. So that's one of the reasons why we think that also the plants have to be protected from the radiation on Mars and that we should go below ground. Of course, that is solvable. Well, and then go back to the food and also the radiation. We can use food as well to protect ourselves against the radiation because vitamin E and C can protect us from the free radicals that you get in the cells when you are suffering from radiation. So, for instance, citrus fruits could help because there's a lot of vitamin E and C in it. But the problem is, of course, that there are trees, and trees need space, and we haven't done any experiments with that because it's not very efficient, and you have to wait several years before you can even harvest the first fruits. But it could help humans to stay healthy on Mars. And another option is strawberries. I like them very much, so I would go for that. But the problem is that it is quite inefficient to grow strawberries. They need a quite long growing period, and it's not very easy to grow them. So we're looking into that, but yeah, we're not there yet to see how we can implement that in the food we could grow on the Mars soil simulant. And then one last, which also I think could benefit. This is bamboo. It's growing in my own garden. I took this picture a couple of hours ago. It's very fast growing. It grows everywhere. Of course, you can eat tips, but I do want to use it for something else because I think a Martian bunker or dome will be very technical. And I think it would help if at least some of the furniture you can make is made of something organic, and then I think bamboo could be one of the plants that can be used. They use it in Asia as well. You could build all kinds of furniture of it. So if that grows, and we haven't tried it yet, but I think it will, then this also could, I think, contribute to the well-behaving behavior of humans on Mars and make it a more happy place to live. Well, and this is some information, and look especially at the QR code that is to our crowdfunding, because all of our experiments are funded by crowdfunding and not by the government. Thank you for your attention.
Okay, thank you, Wieger. So for the crowdfunding, I just want to draw the attention to the mugs that we are using here. You might recognize the picture on it. It's the Living on Mars dome. It's very beautiful. And you can buy it in our web shop. And all the profit that we get from it will go to the Food for Mars and Moon project from Wieger. So, do you have any questions for Wieger?
Yeah, we certainly have some questions for Wieger. So one of the questions that arrived was about using aquaponics, and why not bring some earth soil to seed the Martian soil. So I think they are related.
Yes. First about the aquaponics, I totally agree. We only do our experiments with Mars soil simulant, but in my view, it will be that you have both. And that you do aquaponics. For instance, tomatoes grow very well on aquaponics, so you use that as well. But potatoes is much more difficult to grow it on aquaponics, and I think we will need that. Other crops are also much more difficult. And also, if you have both systems, then if one system fails, you still have the other. So you always have a backup. Of course, you will have compartments also to be sure that if one compartment fails, you still have crops from the other ones. But it's also something about risk and risk spreading. But I think you should use both. But we only do investigation on the Mars soil simulant. And then to bringing Earth soil, yes, you could do so. But of course, it's heavy. It takes a lot of space. And you have to sterilize it, because if you bring just earth soil, there are of course all the bacteria inside, but also the diseases, and you don't want to bring them. You only want to bring the bacteria you pick. So you could bring sterile soil, but if you want to have a proper harvest, you still, I think, need to use the Martian regolith to grow crops in. Otherwise, you have to bring a lot of soil. And I can imagine that there will be some opposition here on Earth if you want to bring a lot of soil to Mars. Even if it is only a relative small part, but I think that, people will just oppose to it. But yeah, and I don't think you need it. So you can make your own soil in the end on Mars.
Okay, thank you for your answer, Wieger, and for your interesting lecture. Of course, very important to get the food right on Mars. So thank you very much, and good luck with your project.
Thank you.
So now I'd like to introduce our next two speakers. We have Federico Monaco, he's a sociologist at Parma University. And we have Carlo Ivaldi, he is a student anthropology at Leiden University. And they will talk about socio-cultural environments for space communities design, which will help people to live happily in extreme conditions. So if you wonder if happiness on Earth will be the same, or happiness on Mars will be the same as happiness on Earth, stay tuned. Okay, welcome Federico and Carlo.
Thank you, Annemiek. So I will start. Sorry, let me try to make this wider. All right, we have it. So, all right, as Annemiek said, I'm Carlo. I'm a master's student of cultural anthropology and development sociology at Leiden University. And together with Federico, we wonder like how to pursue happiness on Mars. So here is our red planet. You can spin it. You can do whatever you want with it. You can entertain yourself while I'm talking. I share with you the slides on YouTube. So if you're bothered by my presentation, you can entertain yourself in that way. So how to pursue happiness on Mars? Well, we decided and we thought to start from some models of happiness that are based on perspective of human conditions, habitats, or identities where happiness manifests. And we try to understand what we can transfer from Earth as virtuous examples of social and individual happiness. And I was having like a chat with a friend a few days ago, and we thought that like going to Mars can be compared to going living by your own. So you have to leave your family behind, and Earth represents like our home family. Which protects us. It's where we can find food and all the comforts that we need. But until we don't move from this condition, we will have to do everything. So until we don't move from this condition, we will have to understand how to do these things by our own. So learning how to cook, how to do your laundry, and in the case of Mars, even producing your oxygen. So until we don't do this, we will not develop the skill necessary to live without Earth. So I would like to start from the very beginning. So the journey, so going away from our home. So we have a first phase, the journey of Mars. And I would like to discuss the Lebedev case, who was a cosmonaut who wrote a diary in 1982 about his staying in space for a long duration. So this represents the first anthropological fieldwork notes concerning human staying in space. He stayed on board Salyut 7 space station, a Russian space station, for around 211 days, which basically is 7 months and represents the journey to Mars in length. And by citing his work, Russian researchers have marked 3 different stages of human condition in long duration in outer space. So the first one is extra surprise and adjustment. So already, as Lucas has discussed before, like the condition in space produce astonishment. So seeing Earth from a different perspective and also the absence of gravity would definitely create astonishment, but also adjustment. So according to Lebedev, it took him around 2 months to adjust to this situation. And after that, unfortunately, there is an increase in fatigue and decrease in motivation, which is also called asthenia, and then can provoke depression, anxiety, and of course, lack of motivation, but also boredom. And you might think, okay, but after a while we'll get used to this. But unfortunately, no, this is reported to worsen. Of course, this is still a happy and healthy living on Mars conference. So that's why we have to get there. So we have to survive the journey to get there and find our happiness. And that's what brings me to the second phase. So the small group settlements. We had some examples of dynamics and reproduction of possible dynamics of crew settlements on Mars. And these are the cases I want to show are a Biosphere 2.0, which is a replica of our Earth biosphere, situated in Arizona, where we can find inside a dome, we can find savanna, deserts, forests, oceans, all the natural environment that we already have on Earth. And inside this place, a crew of 8 people stayed for 2 years between 91 and 93, trying to survive with all the resources they had at their disposal. The second case is Mars 500, which is a research station created in Russia in 2010, where 6 astronauts remain closed inside for 500 days in what were analog Martian modules. And finally, we have the High Seas station in Hawaii, you might already know. It's where NASA conducts scientific experiments, but also crew dynamic studies. So these 3 cases reveal some problematic and some commonalities also in the alligator factors, luckily. So first thing, of course, food limitation. The production of food, of course, is complicated, as Viger just said. And also the type of food that we can eat is limited, and the calories have to be controlled, and so the supplies that we have. So you cannot eat whatever you want. You cannot eat your pasta or pizza whenever you want. And yes, as a good Italian, I will probably not go to Mars if I don't get my spaghetti. But luckily, as Vicar said, we are working in that direction. So let's support him. And second point that has been registered by the crew members of this experiment is a stressful workload. Of course, they had to do a lot of work, doing experiments, writing reports, talking with media, farming as well, and maintaining the equipment. And on Mars, we can imagine that this would be the same, since nobody else would do the job but the crew. And this is a life matter, so the success of the mission would depend on the work of the crew. And then another problematic is raised by the Ascendam syndrome, which is not a Pink Floyd song syndrome, unfortunately. That would be lovely. But this consisted in the alienation and miscommunication that the crew had with the ground control. So this represented a misunderstanding of the condition of the crew, and provoked the desire of more autonomy on the side of the crew, and also decrease of the good morale. Finally, we have the cabin fever effect, which is caused by sharing the same space for a long duration with a small group of people, especially in relation to the annoyance of someone's presence that we cannot escape. So we have to make sure that we go with someone that we really like. But okay, finally, we reached to some good aspects of the alligator factors, and all the crew members reported to feeling an historic importance in what they were doing. So they had the feeling to produce something in the advancement and in development of Martian exploration. So we can imagine that the first crew of Mars, of course, will experience this even on a higher level, considering they will be pioneers of the first Martian colonies. That having a private space, of course, helping to prevent the cabin fever effect that I already mentioned. And it has been reported by the crew members that they prefer spending more and more time by themselves in the private space throughout the mission. So the longer the mission, the longer time they spend by themselves. But still, this left some room for social activities. And so many activities have been used to alleviate to alleviate the stress. For example, art projects, or playing music, play video games. Like in the middle, you see the Mars 500 crews. I think they're playing Guitar Hero. But also they organize parties and conviviality moments. So you can imagine that on Mars party would be amazing, considering the microgravity. I don't know. I just imagine a dancing floor with microgravity would be very cool. Anyway, the final point is feeling part of a larger whole. And this concerns the idea of part of a system of which we are responsible for. So the crew members felt that everything was depending on their action, and as they reported, like the inhabiting a closed system gave them a sense of responsibility that empowered their decisions, but also made them feeling part of a living system in which they had total control. So this leads to the third phase. We settle with small crews, and we finally want to build a larger society. And how do we do that? Well, that's quite complicated actually, because we don't have any experiment, but we can base some thoughts on what we already know. So which are the happiest countries and the happiest societies that we know so far on Earth? So since 2012, based on the World Happiness Report, we know that the 10 happiest country, within the 10 happiest country in the world, we have all the Nordic and Scandinavian country. So this represents a Nordic exceptionalism. And what makes them peculiar, what makes them virtuous, are three specific points that have been underlined by all the citizens. So the first one is the democratic and delivery quality, which represents the quality of institutions, of course, how they try to minimize corruption and also maximize the participation of the citizens, and so how to maximize the representation in the decision they make. And this creates a sense of trust and of course that can extend also in the sociality. So people trust their government, but at the same time generate a sense of community, so being part of the same community, which materialize in social and horizontal trust. So when people care about each other, that's very simple, and care and trust about each other, there are more stable bases on which building public support, so to promote various public goods and also welfare benefit programs. And of course, this can increase the connectedness with other people, but also having good social relationship that can create a common good. And on Mars, I think this will be very important to have a general common good and a very strong social community. And finally, we get to the freedom of making life choices. So this represents this extent to which a country is able to provide to individuals a sense of agency and also freedom and autonomy in the decision they can make. So, in conclusion, well, we can say that building the key factors are building a government that is trustworthy, so they can function as well, but also building a sense of community. So I think these are the most crucial steps that we have to take in consideration, take into account to create a society that works towards the happiness of people. And this can happen despite the weather. So Scandinavian countries are not famous for sure, they're not famous for their climate. So we shouldn't fear the Martian cold. I will now give the floor to Federico, who will discuss the Dutch model of happiness, let's say in honor of the Mars Society Netherlands. So we just give him the screen.
I think you're muted.
Yeah, thank you. Hello, everybody. We came up with the Dutch model of happiness, which we thought was a better way to respond to the needs that we're discussing, because the Dutch model of happiness is a model that is highly sustainable, because it's considering the environment and the Dutch people. They have been terraforming their country for 400 years, thanks to the lakes and creating the polders, so they could run agriculture and really get the land to the sea. Then their lifestyle and also the way they consider small things is, I think, is quite appropriate to what we're talking about, because we're really talking about anything that can be sustainable in a way that can be small as being talking about a small communities, about small environments, and the possibility to run also crops in small quantities. So the idea was to have this metaphor of the Dutch houseboats, and the way they run the people they run their lives on the houseboats. Then the next step we were facing was about the imaginary. So what about the science fiction depicting and representing happiness in science fiction movies? And of course we came out with The Martian, but also with another movie, Castaway. So the question we were asking to ourselves was, is happiness in a certain condition in a fiction depicted as in an individual or a social condition, in the sense that we look for happiness because we look for the others as well, but also we look for something that can really answer to us. So for instance, in the scene on The Martian, when the astronaut left on Mars can grow his own crop, he's very happy because he's been succeeding, and so it is a good moment in the movie. Another aspect we were dealing with was about how to deal with the pursuit of happiness, which is at the base of all the constitutions of the present world, starting from the one from the United States. And so we came up with Cronon, which is an author that I discovered thanks to Carlo. And I've been taking this paragraph, because it's very interesting. The moment we as people, we go and start an endeavor for a new frontier, is the moment also where we redefine the sense of individualism, the fact that we leave the society we were living in. So that age was Europe, and now it would be the Earth to go to Mars. But then once there, we want to found a new society. We want to found a new world with a community, with these values. And so I think this is a very strong position in establishing the values for the future Martians. And we've been creating a sort of this checklist, possibly for what has to do about ethics and happiness. And the first one is about, should happiness be a human right on Mars? Are people on Mars in need to be happy? So this is the first one. And another one is taken from a philosopher from the 20th century, Wittgenstein, when he says that if a lion could speak, we wouldn't understand him. So we turn it to, if only a Martian could be happy on Mars, in the way that we as Earthling, if we think of Mars, we're not going to be happy because it's a really extreme conditions. But considering once people would be there, and considering the values would be balanced and interpreted as the life is running daily there, they could really develop their sense of happiness based on the values they have there. In fact, only Martian natives might practice and culturally decode something as happiness. This has to do with the native narrative, by the fact that we really have to be in a place and live like the people live there to understand what are their values, what is the most important things, and what is the least. Another fact will be the political one. So how are these people going to establish a social contract in such harsh conditions? Are they going to belong to a contract from a company? Are they going to establish a government? Are they going to be like a colony from the Earth or from nations? Another step would be to understand what are the factors and the conditions that make humans happy. And the next one, happy society on Mars, is it going to be written in a Martian constitution? So the happiness, as it was written in the American Constitution, is it going by the pursuit of happiness phrase, is it going still to be in a Martian constitution? Another step is very interesting because by establishing a new word, we want also to change a bit the rules. We want to really to experiment something new. So the question is, would a matriarchal leadership on Mars lead to more happiness? Because what was a patriarchal model on the Earth hasn't been very successful as far as we know. Then another step is about the happiness as social justice. And the last one is happiness and individual freedom in our condition where collective survival is at risk. Is it possible? I mean, can individual happiness can be something that is over the need for a group to survive? The matter about happiness and biology has to do with, of course, as animals, we need light, food, reproduction, adaptation, and moving. But also as humans and primates, we need also social environment, values, and like it was depicted in the Brave New World book by Aldous Huxley in 1928, are we going to create a perfect society by pills to increase the dopamine levels? So is it just going to be a sort of chemical happiness there? Because we need to be happy, and so it's going to be designed as just as a therapy. So the question is, are we going towards an engineering of happiness to survive on Mars? And the factors we have already is it should be a small community. Sustainability should be a must. Then some elements from nature that could be like plants or pets should be present in order to give us the touch, the feel to a certain nature condition. Then privacy to keep our individual freedom still. Altruism in a way that we should be put in the condition to help each other to establish the sense of a community. Then, of course, the food, but also things like a religion, a faith would be really important. The leisure time and also the need to spend time together in a nice way, like parties and gatherings, and of course sex. So how is it going to be about sex on Mars? Because nobody is talking about it. So that's it. Is it a happy ending? Don't forget to visit the website we have created just to hint about all these matters, and we're sharing a bit of references. Thank you.
Okay, thank you for your lecture. We have some question for you. It's about stress between intercultural differences in the crew. Have you thought about this, possibly this problem?
Well, if we're talking about the crew, we're still talking about the mission to Mars. But I think that these people are going to be very well trained, and the matter of culture is a matter of creating a new culture. So it's very hard to define what is the boundary between the cultures we have now on Earth and what could be the cultures once on Mars, because already now we have a really rethinking of what are the let's say the different ethnics. So it's we really need a philosophy more than a cultural problem on Mars to define how to deal with peace and good living among people on Mars.
Yes, if I can add
Okay,
something.
thank you.
Oh, sorry.
Okay.
If I can add something also, if we consider the Mars society itself, we see that people interested in going to Mars are from all the world, spread from all the world. So we have chapters in Kenya, we have chapters in South America, and I think the goal of Mars can unify a community. So the goal, I think, can help in going over these boundaries, cultural boundaries.
So yeah, there are more questions, and like in a lot of science fiction movies, we see the us versus them dichotomy popping up, and this is typically a cause for huge disasters and people dying and exploding Martian domes and whatever. So what are the psychological factors behind it, and how can we alleviate such problems between people?
Well, I think that we can't, because of course and a mission to Mars, at least the first ones, they're going to be quite tough. It's not good to if reaching the moon was not easy, as Lucas Viglietti was showing us. Going to Mars, at least for the first people and for the first astronauts, won't be so easy. But what I think is the big message is a message of hope. The fact that even if on Earth we have so many problems with the climate change, with the overpopulation, with wars, the fact that we can really go out and reach for a new planet is a message of hope. Then it doesn't matter if the scenarios can be dystopic or utopian, but the fact that we are having a second chance is a good way to really to deal with the future.
And you also mentioned the people who, well, not discovered America, but more or less migrated to America, the colonists. And so are there lessons learned from earlier colonizations of other continents and how they can apply to colonizing Mars?
It looks like that according to also to the last discoveries in paleoanthropology, is that what is really is the core of being human is the fact of being nomads, of moving, going someplace else, looking for. So we're sort of all like Ulysses, but the Homo sapiens has been really discovering the Earth. It's been moving around just to look for new countries, for new land, and so somehow we are still on this way, and this is a kind of is saying as is a matter of evolution. So we're moving to a civilization one that we're really want to colonize our solar system.
Okay, so those were the questions. Thank you very much. I think personally, I would need the chemical happiness from the book of Aldous Huxley in the beginning, especially. But thank you for your lecture, and good luck with your research, both of you. So we'll now have a break for 10 minutes, I think. And we'll see you back. What time is it? About 8:45. Yeah, we'll see you back at 8:45.
Hi, welcome back everybody here from the headquarters where we are at Navarra. You can see the logo up there. Navarra is our main sponsor at the moment. And we would like to thank Navarra for also the nice sushi and the technical assistance. And of course, Paul, who is helping us tonight. Navarra is always looking for new qualified software engineers. So you know where to find us now. And let's continue with the Mars conference.
Okay, welcome back, everybody. We'll go on to our next two speakers. We have Mr. Alfredo Munoz. He's a Spanish architect who has designed a cliff city on Mars. And we have Mr. Guillem Anglada, who is a Spanish astronomer who discovered, together with his team, a planet called Proxima Centauri b, which is very impressive, of course. So welcome, Guillem and Alfredo.
Our pleasure. Well, so obviously you can also see that I have this lovely t-shirt that probably you see disappeared in the background of Mars. And this is indeed important. Having a t-shirt means a sense of belonging, a sense of community. And we don't need the t-shirt to survive, but we do need a sense of belonging and a sense of identifying with ourselves with a bigger part of us to be happy. And that's what we are going to be talking about, how design on Mars can actually create happiness. So let's start with it. And while I put together the presentation, I will be explaining that what we are going to be showing you today is part of a design work that we presented last October in the Convention of Mars Society, and that was a multidisciplinary work of over 30 multidisciplinary teams. So basically, we call the city NUWA. And this is the intention to create a permanent settlement on Mars. So in today's talks, we have been talking about how we can be happy on Mars. But the key here is how to be happy long term. We are basically targeting to create a city for permanent settlers. And that has an important factor or criteria to keep in mind. So as I was explaining, we call the city NUWA, and it is meant to accommodate up to 1 million people. But what are the main design aspects that we wanted to incorporate when we created the city? It has to be an exciting place, and we will start from there. And then later, we will explain to you other elements that go hand in hand with that relevance of design into the happiness of its citizens, which is the resiliency and the sustainability that has to be implemented with local resources from Mars. It will not be possible to actually bring things from Earth for a city of the scale that we are talking about. It could be possible for a temporal settlement, but definitely not for a permanent city on Mars. So how are we solving that? Well, we are solving it by creating elements that have very strong character, and at the same time that solve many of the challenges that we face on the surface of Mars. And we talked before about the challenges like radiation and impact from micrometeorites, or even the cold conditions that we have. So the way we are solving it is by going underground, but instead of going on the horizontal level, we are going vertical. So we're going inside the cliff of Mars. There are many cliffs in the planet. So basically, this allows us to bring light inside of the spaces, but do it indirectly. This is critical because, again, we can be safe going underground, but if we don't have the experience of the light, sooner or later we will get depressed. We will not thrive. And this is about thriving as a community and as a society. So the way we are doing it is not only by bringing light, but also to ensure that nature is part of the day-to-day activities. And the way we are integrating nature is to create buffer zones that are between the outside elements on the surface of Mars and the living quarters where the community will be living. And here you can see some visuals of some of those parks that are basically creating the buffer zones. We can see here an opportunity of how the inner spaces from the city of NUA will look like. And again, you can see that not only we feel comfortable and safe, but we also have a relationship with the landscape. And that is, again, important to create a sense of belonging. Why do people want to live in New York or in Amsterdam and not in the middle of nowhere in some random location worldwide? Because there is an identity. We feel that something is strong enough that we want to be part of it. And that's what we try to do with NUA, create an architectural element and a urban city that not only allows for people to be safe, that is fully sustainable and self-sufficient, but at the same time, that is diverse and that is very unique. And by creating the architectural elements that I'm going to be explaining later, and that Guillem will continue a little bit more at the end of the presentation, I think we will be able to explain. But where is NUA? Well, NUA is located in Tempe Mensa, which is one of the big cliffs that are on Mars. And as I explained before, it's basically a vertical city that is excavated on the cliffs of Mars. But the way that we are doing it is we are creating modules. And this is important because, again, we are using materials from Mars. We are not bringing anything from Earth, at least on a conceptual level. So it is important to create a highly scalable solution. But at the same time, we don't want to have the risk of creating modules that are replicated too much, and then every part of the city is the same. And that is one of the mistakes that happened with the urban developments in the 20s and the 30s, and even in the post-Soviet Union, where we have urban plazas and buildings that are all the same. It does not bring that sense of community, that sense of belonging. It does not bring the diversity that is so important for the citizens to thrive and to be happy. So the way we are doing it is we are creating what we call a macro building, which basically comprises different activities. It's like a mixed-use building. It includes the resident quarters, but facilities for the community to interact. It also includes the working areas and art domes and circulation spaces. And every macro building is basically a net of three-dimensional tunnels that are excavated in the rock. That macro building accommodates for 4,440 people and is self-sufficient, which means that on a day-to-day basis, you don't need to actually leave the building to live your life. But then those buildings, as I explained, comprises of tunnels that on average have a diameter of 10 meters and that they go as deep as 150 meters in depth into the actual rock of the cliff. And as I explained, they have different activities. But the modular aspect of the macro building is also comprised of modules, 12 modules that can be recombined. This way, when we are working with the manufacturing of the elements in the city with robotics and artificial intelligence, all we need to do is 12 modules that when they are recombined, they allow for very unique experience, because one macro building will be completely different to the next macro building because they can be comprised of the recombination or the repositioning of the different modules. This also allows for a high level of scalability, because once we have one macro building and is completely full with the citizens, then we continue to the next one. You can see here that as part of those buildings, we have gardens where the community will interact, where we have the natural elements and some animals like butterflies and some small elements of relationship with Earth that bring that experience of nature that our colleagues before explained also how important it is to be having a happy life on Mars. So the sense of community is critical, and we have the common areas where the relationships will be a fundamental anchor for the citizens on Mars. Space is very expensive on Mars, not only to build it, but also to maintain it. We need to ensure the air is properly treated. We need to ensure that the systems used for the construction are efficient. So the way we are solving the lifestyle on Mars is very similar to how we create here on Earth co-living environments, which means that every person has their own private space, which is not big. It's basically 25 square meters per person with their own little villa or their own little pot. And then the rest of the spaces are communal. So enjoyment, dining, kitchen, interacting with the community all happens in these communal spaces. And here you can see a sample of them. And some of them happen in the border of the edge of the cliff, enjoying the landscape of the Martian views. But the city is not only inside the wall. As I explained before, most of the activities happen inside the cliff, but then we also have the opportunity to include elements that are fundamental for the happiness of the community, which are the production of energy, the production of food, and the production of goods, which happen in the mesa, which is at the top part of the cliff, and that you can see here some visual example of the different greenhouses that are integrating with the production of energy that we will explain later. But then we explained before that the macro buildings basically accommodate for the day-to-day activities of the city. But we also have other areas for the community to relate and to socialize on more special occasions. Similar to how we have here on Earth, like public parks or museums or auditoriums or sports arenas. That happens in the valley, which is at the lower part of the cliff. And that is basically comprised of two types of buildings. We have bigger tunnels that connect with the vertical elevatoring system that integrates with the macro buildings and with the mesa. And then we have some domes that provide a relationship with the horizon and a relationship with the Martian landscape. But the challenge that we have on the surface of Mars is that if we just have a glass dome or a polymer dome, it's not really that good for the protection because of the radiation. So the way we are solving it is we are having a very large canopy that is overflying those transparent domes that allow, again, the relationship with the horizon. And then the excavations that we get from the tunnels inside the cliff, we are dumping it on the top of that canopy, providing that level of protection against the micrometeorites impact or the radiation. So here you can see how the relationship with nature, the relationship with animals, and the interactions with the community as a whole for the entire city can start to happen and create a lot of diversity. And again, very important to create identity and to create a sense of belonging in this particular case, clearly understanding that we're on Mars because we are seeing in the far the Martian landscape. Not only, obviously, we can relate to Mars from the cliffs because we are seeing it all the way through at the top of the cliff, but here from the valley as well. And then we basically have different levels of tunnels that interconnect all those spaces. As I explained before, there is a vertical elevatoring system that allows all the different spaces to interconnect. And that is similar to how we do super skyscrapers here on Earth, where we have sky lobbies that basically provide the access to other vertical communication systems that are separate. In this particular case, they are the macro buildings. So we separate circulations, we ensure also security, and we provide the fast speed elevatoring system. But when we look about areas, that is important about how happy we are going to be. Are we going to be really tight and don't have space, or are we going to have a lot of space and therefore have the opportunity to really enjoy a lot? Well, again, building in Mars is very costly, and maintaining that volume of air is very costly as well. So you can see here that the areas that we have on NUA available for humans, that means that humans can go there without a particular suit, is an approx of 169 square meters. And the areas that are not available for humans, like crop manufacturing and production and energy generation, is around 109 square meters. Just to give some context, Manhattan if we compare all the built area in Manhattan, along with all the streets and the parks that obviously people can walk around because the air is the appropriate for humans to do so, we are talking about 160 square meters. So if we compare the environment and the density of NUWA, it will be very similar to a highly dense city on Earth, similar to Manhattan, similar to Hong Kong, potentially a little bit more dense than Singapore. And with that, we are going to continue with Guillaume, that is going to explain how the different cities that we are envisioning can provide, again, a sense of identity and belonging. Guillaume, do you want to go ahead?
Can you hear me?
Yes.
Give me an okay. Okay. So I hope you can see now. One of the issues that Alfredo mentioned at the beginning is that this is not a matter of building a city in a place and then letting it go. It's a matter of trying to think how to develop the city. People is an essential part of the city, but also are the infrastructures. And these infrastructures need to be resilient is one of the things. So one of the things that we need to take care, they need to have access to resources, but there has to be redundancy as well. For example, in our proposal for 1 million people living in Mars is not to put everyone in the same basket, let's say to distribute it in at least 5 locations to really get access to strategic resources. Therefore, the city can grow in a sustainable way, only using resources and only using resources of Mars. This is what I'm going to try to tell you. That's very hard. It's almost impossible to do it from Earth. So you cannot deploy a city of 1 million people just bringing stuff from Earth. As you will see, the numbers later are massive, and you can probably not afford that. You just need to make a city and then let it develop. And therefore, what we try to do in this study is to really see if we can put a decent living standard, if the people, the Martians themselves, can develop and therefore have a full life and therefore a successful city and a community in another planet. So these are the 5 cities that we proposed. NUWA is one of them, near the equator, not exactly the equator. There's one in Valles Marineris, a folkloric place, but also a source for minerals, especially metals. And another one in the pole, an important one, but because that gives you access to a lot of water that it can be mined directly from the surface. This is just a depiction of what Alfredo was also illustrating. Once you have the concept, there are a lot of cliffs. The same machinery can be translated to any other location on the planet as long as you have a cliff with a strong rock. These cliffs, the rock has to have some properties, but in principle, from remote observations, we know that this is the case for example, places in the North Pole where you can directly mine the ice. And this is just an example of a city or a part of a city that would be in a canyon, for example, in Valles Marineris, just a depiction of the same structure being repeated all over the place, again, with the character of each and different location. So apart from having good spaces to move around, of course, happiness depends on how good or how well you are fed. And we had a specialist in the team looking at the diet of the people in very general terms, again, not person by person, of course, it would depend a lot on diversities and things that people like, but ideally the diet of a Martian person to be more or less optimal for a number of reasons is something like what you would see here. You would need a lot of crops, meat, as much vegetables as possible, and microalgae, for example, use bacteria for recycling, and also grow some stuff in the lab, for example, cellular meat, things that are being developed, or bioreactors, and even still have some food, some animals, sorry. So animals serve first a psychological thing. We want to have pets, we want to have contact, grow animals, at least in the current human status, but also they serve as a buffer. When there is more biomass that it's being able to be processed, you give it to the pigs, as it was done in the Middle Ages all over the world. And these pigs act as a buffer. When you need that, then you just consume it. For example, that would be life support system, of course, then you need to process the air, etc. We are not going into a lot of detail today, just to mention things related directly to happiness of people. And this is just a depiction of one of these greenhouses, which would be at lower pressure than in the habitable places with more fraction of CO2, because then plants grow faster and also it's easier to keep the pressure under these environments. Of course, most of the light needs to be artificial because the light energy density on the surface of Mars is lower. Therefore, the food needs to be grown pumping energy into the greenhouses. This is just a depiction. You can see this bluish light. Yes, all these greenhouses, again, Alfredo showed you, this is urbanism. It's not just cities, it's actually deploying all the infrastructure. You have the city where people live. You also need the industrial areas, energy production. In our design, this is put on top of these mesas, so people don't see all the time all these panels and all these things. They know that they are there, very close to the city, so they can go to work, but they don't necessarily experience the solar panels every day. There's no need for that. But then, of course, that requires a lot of surface. It can also be done with nuclear energy, which has to be there also for a matter of resilience. In case there is a blackout because of a sandstorm, we want to be sure that we have at least enough energy to keep people alive.
Guillaume.
Yes.
Sorry, Guillaume, can I just interrupt because your presentation is not shown on YouTube right now.
Oh, okay. Sorry. I can stop
So
sharing.
it's shown.
I can share again. Can you see it now?
Yeah.
Yes, now we see the right picture. So yeah, we don't see you yourself. It's
Wow.
like you haven't your camera on YouTube, but you have. We have seen that you have. So
it's all right.
If that's not a problem, you can continue.
Sure, it's fine. It's fine. No worries. It's better that you see the pictures. So anyway, so here you can see just a bit of a distribution of how you would have photovoltaics, but not depend too much on them because you need semiconductors, and semiconductors are difficult to manufacture on Mars. Mostly solar concentration for the bulk of the energy required to develop the city, and nuclear to provide this threshold of energy that keeps the city alive all the time, for example. And of course, then the food. I'll go later into a number that was here shown for the first time, but you will see later. Another thing that you need as well, again, it's a city, it's a system, it's an economy, it's a political organization. You need, apart from people being happy, part of the happiness is about people being able to develop their own passion, organize themselves to create an economy, to have an incentive. And that's, again, the contraposition with a pure communist system or a pure capitalist system. There has to be a balance. So to keep people motivated to go there to experience the community, but also to be able to develop their own interests. So for this, we proposed a system based on a coin. When surplus infrastructure is created, let's say the city council gives coins to people that have shares. Every citizen has city shares, but also they can acquire them, but then people can associate, share these coins, put them together, and, for example, create companies, create organizations, and go back to the city council to, for example, buy infrastructure. Always this surplus, always work with surplus infrastructure. Therefore, we created now something that has value on Mars. People can work to create their own businesses, to create excursions, to make a restaurant, and to create a soccer team if they want and organize themselves. So that's kind of how we propose to nucleate this Martian economy that also should lead to people's happiness. And a very important part of the concept, and that's the last thing we are going to show, is what we developed, something that's called the city unit, which is essentially the human and all the materials, infrastructure, machines, everything that needs to be incorporated into the city in order to put one human. So that means atmosphere, it means water, but also the machinery associated to this, etc., etc. So the process of doing all these things that Alfredo showed you the city. We also kind of scale the industry, try to estimate how many machines we need for everything that is needed. This is a bit summarized. Well, it's summarized here, doesn't matter, sorry. But then, of course, we know how to do this on Earth. Then we had to find the Martian equivalence that includes some overheads in energy. Energy is the currency that allows you to do things on Mars and on Earth as well, but we are not very aware of this. But energy is essential, is the basic currency of the planet, not the euro or the dollar. So with energy, you can transform everything into anything else, essentially, and you have the same components on Mars, but you need to put everything into place with big spreadsheets, account for everything, every single joule that is needed. And when you do this, you end up with something we call the city unit budget, which is what you saw here. It is a very busy picture, don't want to go into details, but the key points is that to include one human requires essentially 1,300 tons of mineral being mined from the planet, requires around 80 tons of water and CO and 113 tons of CO2 collected from the atmosphere. This is usually actually to fabricate organics and materials, not to drink. Actually, the drinking water is not much of this budget. And the most important thing, again, for the well-being of people is that, for example, is needed 117 kilowatts of power per person. This is to keep the development rate. If you don't want to develop the city, just keep it alive, you need around 40 kilowatts. But still, this is a big number. If you compare it to Earth, this is about between 5 and 10 times more than what is needed in a country like the US, a developed country, or European countries. So what we do with this extra power? This is a red flag that comes out of the design. It's something we wanted to identify and we found it. It also means that each person has to operate machinery or do work 10 times more than a person would do on Earth. Of course, that would cause a lot of stress to our pretended happy inhabitants of Mars. So we have to sort this out. This absolutely will require this new level of automation, this new level of standardization of all the procedures. You don't design farms and then put some farmers and then substitute by robots. No, you design directly the infrastructures to be operated robotically and with the support of artificial intelligence. We are a factor of 10 off. In this sense, that's the technology that is actually more critical at this point, more than even the processes to make the materials. At least this is what we identified. Again, also very important to actually motivate. We want people to go to Mars, to live on Mars, not to force labor people there. So to have this motivation, they really need to know that when they get there, they will have a happy and not super busy life. And with all this said, let's see, I'll put a video that will give you more the experience of how NUA would look like. And see the team.
We don't hear the sound.
It's okay. The visuals are coming soon. With the visuals, it will be enough for everyone to get an idea, and then anyone interested can always Google NUA, and then the video is available all over.
Yes. Just to get a feeling of the spaces in motion, which helps, again, to feel the city in your tummy, which is what really matters at the end.
The music helps to bring the experience in, but unfortunately, since that doesn't work, but still we will make it happen. It will give a decent, fair idea.
Okay, we are done. Thank you very much.
So that is quite a vision you put here. It's a complete picture of a city, which, by the way, looks stunning. I really love it. And there's also a very interesting conclusion, and the conclusion is we need more artificial intelligence, which was exactly, or not exactly what I expected, being an AI expert myself, that you would have this conclusion. Besides that last point, I think a lot of people are wondering what would be the timeline to develop such a city. We see this in 2050, 2100. Do you have any idea?
You want to jump on it, Guillem? Then can give
I'll
my
start.
opinion.
So the issue is when to deploy. First, we need to deploy the city infrastructure. This can happen, I would say, in 2 decades. That's already the thing that is being discussed. So this city infrastructure, the first 1,000 people that will start the thing. When this is running, is actually being done on Mars, so it doesn't cost much more to Earth. That's a good thing. But of course, then it needs to fabricate everything by itself. And then this sets the power requirements, actually. So we estimated that to make it in 50 years, we need this 117 kilowatts, which is this factor of 10 times more energy than a citizen on Earth. You can reduce this number by extending the baseline. Instead of 50 years, do it in 100, for example. Then you reduce the power consumption. It's not entirely true, because there's the maintenance, just to keep people alive, costs you 40 kilowatts, especially to feed the plants. That's the worst thing. The production of food is the one that consumes more energy, actually.
And to add to what Guillem just mentioned, there are some critical paths that obviously can affect to the implementation. As we explained, NUA is very based on tunneling system. So in order to be able to actually start the execution of tunnels, we will need astronauts verifying that the locations that we have identified can be actually used. So until we don't have astronauts on Mars, that's something that cannot be done with the vision that we have for the city. So we are currently working on protocols on how to create analogs here on Earth about those type of tunnels. So there are some critical paths that we know have to be solved. Obviously, the artificial intelligence and robotics within the industry is going at a very good pace. But we are, just to give a year, we are envisioning that, being optimistic, the city could start in 30 to 50 years. And with the growth speed that Guillaume was saying, potentially could be almost finished by 2100. We know it's optimistic, but yes, it gives a little bit more of a time frame on a particular number that I guess that the person that asked was interested in knowing.
Okay, I would like to ask about the bamboo that Wieger was talking about earlier. What is your view on using natural materials in the interior on Mars?
Very much indeed. That was one of the things that we consider. We did not have the time to explore further the interior spaces along of what you have seen, but we definitely believe bamboo is a material that has a lot of potential. We have used bamboo in the past, and we are very familiar with it in Asia. So we are strong believers that natural elements should not be only part of the landscape, but also should be part of the day-to-day experience of the space.
Yeah. Also, just a comment that as a material itself, these all biomaterials are very useful, because you might think that the plant is not very efficient transforming energy into material, but when you think about a wall, a modern wall of a house, all the different processes that have to go there, all the industrial complexity that sometimes go into making just a beam of something, if that can be replaced by a plant growing, sometimes this inefficiency in the energy, you get a much better performance actually it's not always trying to get the best material, sometimes it's trying to look at the processes as a whole. That's a very important thing. And bamboo, for example, would fit these for interior spaces, and we have all these tunnels, essentially domes, that still need very advanced materials as much as we can, but everything inside, it's a bit of also the idea of NUA. You create urbanization, you create the volumes, and then people do a bit whatever they want.
And I think as a last question, since it seems that everything boils down to getting enough energy over there, and there is not so much sunlight, and even here on Earth, solar panels are not always that useful. So how do we get all that energy on Mars? Where does it come from?
Guillaume, go for it.
Well, energy, it's a matter of building larger solar panel fields, and also probably developing nuclear energy that it can be, again, supported and developed on Mars. I'm not a supporter of nuclear energy, but I'm not against it either. It's not very popular, especially in Europe, to discuss use of nuclear things on space, but it's a reality that in Mars is kind of the most practical thing that you can do, is where you can pack more energy in less space. It's not true, again, that a nuclear plant would solve all your problems. Just building the plant, again, requires a lot of technological complexity to maintain it. But for example, if you can build several small reactors and only the feasible material can be shipped from Earth, or something like this, some scheme that requires very small amounts of mass that can be transported, not the whole infrastructure, that probably would work. But it has to be a combination of both. On Earth, we are cheating. Be careful. On Earth, we also need all this energy, these 40 kilowatts of energy, but we cheat. What we do, we trade the surface of the planet with the plants. The plants have a transformation efficiency of energy very low, about 1%, 2%, the best ones. So instead of having these very optimal greenhouses, what we have is vast extensions, about 6,000 square meters per person, where on Mars we would live with 100. And then actually all these fields, what they are doing is collecting energy. That in Mars we are doing it synthetically. That's the trick. That's where the number comes a bit surprisingly high.
And just to give a bit more specifics about NUA, 70% of the energy that we estimated, we obtain it through solar, and 30% through nuclear. Is also because of the dust storms that we will not be able to leverage the sun during those times that can be very long. Just to give also a context of the areas in NUA, which is the capital of the entire settlement of 1 million people, which accommodates around 200 to 250,000 people, the solar energy takes 75 square kilometers in area, which is pretty large. So again, it gives a context of areas when we're comparing with Earth, as Guillem was explaining.
Okay, so Alfredo, I would like to thank you for drawing your attention, or everybody's attention, to your T-shirt. Could you please stand up one more time and try to show it?
Of course. Let's see, Mars. Let me show it. There you go.
Listen.
That beautiful T-shirt you guys created.
Yeah.
We're part of the family now, like everyone watching. Again, sense of community. That makes me happy. I'm sure it makes everyone happy here joining us today.
Yes. Thank you for pointing out that design and identity are important. So everybody can buy this T-shirt in our web shop. It's marssociety.space. And I would like to thank you, both of you, for your beautiful presentation. Thank you very much.
Thank you very much for having us.
A pleasure.
So we'll go on to our next speaker. It's Dr. Nikki Hexter from IBM. And Dr. Hexter is working to solve challenges in healthcare and life sciences with the help of AI, or artificial intelligence. And in his lecture, he will talk about how AI can support people who are far away from home, like astronauts, and have medical problems. And of course, we all wonder if the technologies used in Star Trek could be real one day. So welcome, Nikki.
Thank you. You can all hear me, and see my presentation? Please confirm.
Yes.
Okay. And I'm also wearing the T-shirt, so I'm part of the community, as was pointed out by the previous speaker. So thank you for being the last speaker in this tremendous row and awesome presentations. I listened very carefully and with interest. And well, I'm happy to say something about how to manage healthcare and health in space by means of artificial intelligence. So let me first introduce myself. So my name is Nikki Hexter. I work for IBM Watson Health. So this has to do with AI and health and healthcare and life sciences in general. And Watson is a name of a platform that IBM uses for AI throughout the world, and was one of the first commercially available platforms in 2011. And what I do is business development across Europe. So that's me, if you want to call me or write me later. Well, IBM has a history in space, you know. So when Matej asked me to do this presentation, I was immediately in for it, because yeah, IBM and space, that goes together very well, you know, from the early beginning, where we are looking at early programmed calculators and punch cards even, to bring the Apollo mission to a success, where they used our big computers and software. Up till now, in the Mars rovers, you know, there are the chips inside from IBM, and I think we have the largest market share in Mars at this moment in time, although we don't send salespeople commercially to Mars at this point. But even the Perseverance, who is now wandering over the surface of Mars, has AI capabilities inside to recognize certain objects in images that have been taken. And even we are using supercomputers to simulate, of course, a lot of things. And yeah, I will talk more deeply about Simon. You see that in yellow. Simon in space, and that's the first free-flying AI-assisted robot, so to speak, to help the crew of ISS. Now, when you think of AI, probably you've heard of it, artificial intelligence, and I will give you some sort of definition later on. But a lot of people think of familiar robots that you know from Hollywood. And that's the ultimate version maybe of AI, because what AI really is after is mimicking our thinking, our senses of human beings onto a machine, onto a piece of software. But this was already the thinking in the mind of Isaac Asimov. I don't know if you know him, but he is a famous American-Russian science fiction writer who did a book, I, Robot, already in the 40s, where actually these robots were used in space to mine, for instance, minerals from the planet of Mercury. So this is, and there are many more applications there, and it's a very interesting book because it also highlights the ethical side of using robots together with humans. But again, it's about robots. And Hollywood is very much into this. You see below I, Robot, that's a movie made recently, which is a remake, more or less, of what Asimov wrote down. It's a bit scary. And you mentioned already Star Trek. Yes, Star Trek was also, of course, a very famous series where the scriptwriters already had some ideas how it would be to live in space and what you need to do. And they had a couple of ideas that now, are realized actually. But it always highlights in Hollywood the more scary side of AI. And why do we do that? Yeah, of course, if otherwise nobody would come to the movies and to see them, because if it's a happy story and not scary, okay, you want to have some emotions, some sensation. And also a nice movie, I don't know if you know it, is the 2001 A Space Odyssey. And there's a computer featuring called HAL 9000. And as a matter of fact, if you move each of these letters, HAL, one place in the alphabet, you get I, A becomes B, and L becomes M. So it's IBM. And that's done on purpose because the scriptwriters of this movie, they came to visit us and they were impressed with what we could do with natural language processing and computational linguistics. And those were the first steps into artificial intelligence and then apply to natural language. And as a matter of fact, this computer can lip read, and I won't tell you the plot if you don't know the movie. It's really a classic, but also a little bit of scary end. And this is the tricorder in Star Trek, you know, just to highlight the ideas that people had at the time already to do something at a distance. For instance, triaging patients. Somebody is suffering from something, then they had this device, and he could do a lot of more with the tricorder. But it's coming of age now, this technology, actually, as a matter of fact. And AI is there in your daily life. Maybe if you are using Google, and I'm sure you are doing that, then basically you're training a machine learning system, because you get the products from Google for free. That means that you are the product yourself, because you are using these products, and with that you are training a system at the back. And but there are many more, like spam filters, or maybe you are into genealogy with MyHeritage. You can bring old pictures to life, even movies again, and improve them with the help of AI. Color them, for instance. You see Siri here, and Siri is also an example of AI with voice interaction. And you see at this point, I asked Siri, I said to Siri, I have an alcohol poisoning, what can I do? And he comes back with 7 liquor stores in my neighborhood. Okay, so you see that these systems need to learn still, but they learn from the data and they improve from the data. And well, there are many more papers in the articles of papers like the New York Times. Some of them are written actually with the help of AI. So you just give keywords and a couple of clues, and then out comes automatically a very realistic article. So there are many more of these applications, even paintings. You can mimic paintings of Rembrandt or Van Gogh with the help of AI. Okay, so artificial intelligence is really the creation of intelligent machines that work and respond like us humans. And you can apply AI in homes with sensors, as the previous speakers have pointed out. And they learn actually from the data, and they take decisions based on the data and based on the observations. And what you really do with AI is recycling human knowledge and human intelligence, and use that in other cases. And because of computers are much more powerful than our gray supercomputer here in our head, AI gives some astonishing results. For instance, Google has written a program that defeated the best Go player in the world, and Go is much more difficult than chess, for instance. IBM did it with chess, but Go was done with Google. It's a 19 by 19 board, and it's really difficult to do that. But they applied some techniques from artificial intelligence and really defeated the best Go player. And the astonishing thing is that the computer came up with some strategies that had never seen before by any Go player in the world, because it could go through so many options and learn from the different strategies that others had performed, that it came up with something entirely new, because it goes beyond our human brain. And AI is really a confluence of different sciences like informatics and mathematics, but also ethical sides of AI. You need to deal with that, and that's also something maybe that if we are going to apply it in space, for instance, with robots, that you need to consider also the ethical sides of AI. So there's many things come together here. Now, really, AI is augmenting the human sense. So we are not replacing humans by this, because this supercomputer in our head is still much more better than any AI system. I mean, we can read, we can speak different languages, we can do mathematics, but these AI systems most of the time are very narrow. They do one thing, but they do it extremely good, extremely good. And there are several techniques like natural language processing. So I just told you about that. You've probably heard about machine learning, and there are many of these other techniques. I won't go into them. But the applications that you can conceive with them are very powerful, like text comprehension, but also text synthesis. So there are many applications that go from speech to text and text to speech. So you can actually let a robot or a chatbot speak. You can interpret images. So if you are a doctor and you're looking at an image by the end of the day and you get a little bit tired, then maybe AI taps you on the shoulder and says, hey, you need to look at this part of the picture because you missed that in your annotation. And those are real applications today, you know, and it's even so that these systems are able to write software automatically. So in the future, we will see that these systems have learned from millions of lines of code and can write their own stuff, and that will be something very new, and but maybe a little bit scary that they are going to do something on their own. Anyway, so what's happening with healthcare? So that's AI, and there's a little bit of introduction in what IBM does with NASA and space, and IBM is working hard on artificial intelligence, of course. But there is something else in the world going on, and that's the digital transformation, and that's for all sectors, especially for healthcare and life sciences. So we are talking a lot about the e-health, which makes a person, a citizen, a patient, more powerful by means of apps, for instance, or any other tools, maybe a portal, other digital means. And at the other side, we have digital health, and that's more the doctor side or the health professional side, who also uses technology to make the life of a patient better, or decide on the best clinical pathway, or do some advanced research, you know, and what we see is that the society in healthcare or healthcare moves from a hierarchical society to a more collaborative partnership. So a lot of patients or citizens are working together actually with research institutes, even with hospitals, if they are seen there by doctors, by making use of this technology that integrates data and bring a lot of data together. And with that, you can make healthcare much more personalized and much more precise. So we have applications of chatbots and wearables and implants to actually robots. Robots that on the one hand can be used for elderly people to make their life more easy, to ban loneliness, for instance, to robots that actually perform surgery and everything in between. So what is done there is that we are really capturing the knowledge of what we have been publishing in the world as a medical society, but also, of course, the knowledge of the doctors and the data we get from new experience, new patients, and that all comes together through AI. And with that, we try to do the best for the next patient. So we will see that a couple of those applications. Okay, but what happens in space with respect to healthcare? And people before me already have spoken about food and exercise and psychological and social well-being, very important. Physical conditions, you need to maintain workouts and be fit, of course. But one of the problems we have as an ICT company, of course, is that the time delay. If you go to Mars, then you have time delays from 4 to 20 minutes before the signal comes back. And maybe that's too short in an emergency situation. And well, there is limited amount of medical knowledge and skills. Maybe, I think that Federico and Carlo were talking about having children on Mars. You know, who needs, if you need to help with the delivery of a child, you know, and monitor all kinds of systems. Yeah, that means very advanced equipment, and but there are limited medical devices and supplies and medication. And what if something happens in an emergency procedure? How do you deal with that? Because we don't have the earthly knowledge and equipment at our disposal. So those are really challenges when it comes to healthcare. Well, there are digital health technologies that have been evaluated, at least in one medical study here on Earth, that could help, like virtual reality. You could put up a virtual reality glass and be in another world for a moment to reduce pain or anxiety or help with your social well-being. It could also be augmented reality, because that's already used in surgical practice, where doctors before performing surgery on real patients try to do this in a virtual way, and to see through the patient, even where is the spine, for instance, where are the muscles, or where are parts of the body. Telemedicine, that's of course, because of the delays, a problem. It is something that has been proven. But if you get further away from the Earth, then you have these delays, and telemedicine will be something difficult, but still maybe you can access files that you don't need right now, but maybe over a day. So that could be the case. And there are many more things. Maybe you need to 3D print something because you have, it could be a vital organ that will be 3D printed in the future if you perform an operation. So there are many things. Surgical robots, I already alluded to them. So these are things that are being used on Earth and have been verified. But if you look at IBM, I told you we are very much involved in healthcare, but also Google, Microsoft, Amazon. They are all looking at healthcare through AI glasses, you know, and it's really about recycling the knowledge of healthcare professionals, finding new ways, finding new clinical pathways for patients, finding new drugs, all that stuff. So they're all, if it's about clinical decision making, then yeah, you cannot take a cohort of doctors up in space, but you can take the knowledge of them into space, you know, and have an AI system sort out because on the basis of the knowledge, what would be the best procedure or what would be the best medication. And also medical imaging. There are no, well, maybe there's somebody who knows something about radiology, but of course you need some basic equipment to make an image, a medical image, but this can already be done with with your iPhone with a special equipment attached to it. But you need to interpret, of course, the image, and again, AI can help you there. And yeah, if you want to look up something and find something, then querying like you do on Google is not enough, because you need semantic search, really. You need to know what the context of a medical term is, you know, and there are techniques from AI that help you to do that and go through the medical literature in a very fast way. And you can all have that, of course, in bits and bytes aboard, or maybe in the cloud, somewhere in space. Now, I think that astronauts of the future can wear the same things that we wear Earthlings here today, like Fitbits, so sensors to monitor your health. There, I put down here the Hexoskin Smart Shirt, which has a lot of sensors, and I think that in already astronauts take a lot of sensors in their suit. So, but this becomes more advanced. Yeah, there are even digital stethoscopes. You know, the stethoscope was invented in the 19th century. It's still being used, 1816 to be precise, and it's still being used in every hospital in the world. It's more something for your status as a doctor, you know, that you can show that you are actually a doctor. But it's a very old device, and it can be replaced by something here like the Echo Duo that also can produce an ECG and has AI inside, and that can learn from the patterns and advise on your health. So you see already here a couple of those devices, and there are many more devices that are based on AI. Now, one of the things that I think personally will be one of the big things in a couple of years, not 10 years from now, but maybe 2 and 3 years or 3 years from now, is quantum computing. And those are computers not based on the classical technology we are deploying today, which is inside your laptop or on a server somewhere, but it's based on quantum mechanics. And I can imagine that not everybody of you who's listening has done a course on quantum mechanics, but this is a totally new way of making computers. And a quantum computer can do things much more faster, but they can do it also much more precise. To give you an example, there are cryptographic algorithms to shield bank transactions, which a normal computer would take maybe 100 years to unravel the crypto behind it. These kinds of computers do it in a couple of minutes. You know, so you're bringing back an enormous amount of time back to a couple of seconds or minutes. And this can be used to, for drug discovery. It can be used for personalized medicine. These systems need to be cooled back to the absolute 0 Kelvin point, and they're very sensitive to disturbance from the outside in the context where they are placed. So on the one hand, you think, hey, that's good news because it's minus 270 degrees, .15 in outer space almost. So maybe we can put this in a satellite. But at the same time, radiation will be a disturbing factor there. So I don't know how we are going to do this. But maybe we can put a quantum computing aboard the future missions. And then you have something that even can mimic yourself, because people are thinking of digital twins. So we can mimic ourselves into a simulation model, also based on AI. But you need a very fast and a very precise computer, and that's where quantum computing could give us something. Okay, but let's be closer to Earth for the moment. Go 400 kilometers up. This is what you know, of course, ISS, and we are working already there with AI, not with quantum computers, but with AI. Because we have developed together with Airbus and the German aerospace organization and the Ministry of Economy and Energy, something called SIMON. And SIMON stands for Crew Interactive Mobile Companion. And it's something between a chatbot and a robot. And I told you it's the first flying robot in space. It's actually being used. And yeah, why did we develop this in the first place? So It was brought up to the ISS by a German person, a German researcher called Alexander Gerst. And you see Alexander here doing his projects. He needs to open his iPad, open a PDF maybe, and read what he should do. It's quite cumbersome, and he needs to turn around to grab something, and he needs to do it in the right order. So this was one of the use cases where we thought, together with Airbus and DLR, why can't we have a smart device that would help the people in ISS performing these experiments or doing other things? And that's where we came up with this thing. And here you see some capability and facts of Simon. So it has a camera, it has a display that actually moves. So it moves its eyes and mouth, and can speech to text and text to speech. So it can hear you and speak to you back. It has cameras aboard. It has an infrared camera even, so it can measure temperature, and it can move. It also has propulsion through with air, so it can move up and down and around. And I will show you a little movie in a minute. But this is all powered by artificial intelligence from IBM Watson. And so, yeah, we made this to accompany the experiments, but also to do skill training, to have mobile video documentation. So documentation is very important, and you don't want to look it up in books, in PDFs. But you know, so there were many use case scenarios where they could use it. But there was also a soft call, of course, to what extent such a robot could be part of the crew, and how the people would react to this. So that was also part of the deal. And behind the scenes, is it AI or aboard, or was it in the cloud? Well, actually, the artificial intelligence components were not on the ISS, but it was somewhere in the cloud on Earth. So it's and because it's only 400 kilometers up in the sky, the delay of the information is minimal. But yeah, if you go to Mars, then it's different, of course. Then it will be very different. And but the latency and disturbance, well, we of course thought about this. We need to implement a sophisticated process to reduce the latency. Otherwise, people wouldn't use it, because if you need to wait a long time, then it doesn't make any sense. And yeah, of course, data privacy. If something happened and there was private data included, like yeah, something personal, maybe about an ailment or something else, yeah, then we would shield it, of course. So that's also one thing we thought of. So Simon actually shows human behavior. So it recognizes natural language, and it speaks English, but maybe in the future it can speak different languages at the same time. But it actually talks. So
my mission is to assist you wherever I can, and to motivate you, no matter which task needs to be done.
So I hope you could hear this, but that's the voice of Simon. It can actually talk.
I know we are very far from home. What can I do to cheer you up, Alex?
So you see, he's talking to Alex, and he wants to cheer him up. So social and well-being can also be promoted by such a device. And it actually can see, I told you, there are cameras aboard, and Simon also reacts emotionally. So that's funny that it can do that. So it has really human-like behavior. So yeah, we designed this with consistency in mind, and it's really modest, introvert, sensitive thinking and judging. So it's an ISTG, as it is called. And yeah, it has intonation aboard also. So speech to text normally is computer voice, which is very monotone, but it doesn't do that. The intonation is very important here. And these facial expressions, you see one of them here, and movements. So it really looks like if you are talking to yeah, a humanoid being. So let me show you a movie in this.
You're going to some configuration steps now. Simon, wake up.
I'm waiting for your command.
Pretty good at listening. Pitch down 40 degrees.
Wilco, pitch down by 40.
Simon, rotate right 90 degrees.
Okay, turning right by 90 degrees.
Okay, well, that was pretty good. Pretty consistent. How is the weather in Catania, Italy?
The current weather in Catania, Italy, is partly cloudy at 18 degrees Celsius.
Simon, what can you do for me?
We can do skill training with the Rubik's Cube, or do some other cognitive training by playing games. I can assist you with instructions for the experiments and act as a mobile camera.
Simon, move to Biolab.
Wilco, moving to the Biolab.
Can you help me with a procedure?
Which procedure exactly should I open?
Help me with the EPO crystallization procedure.
I suggest to start with the big picture words.
Tell me a fact about history. Move forward by 30 centimeters.
The particle crystal will decompose slowly as the electrical charge is lost over time.
Next.
When the kinetic energy dissipates before the crystal is formed, the beads might stick to the wall and form a crystal there.
Tell me something about space.
The Apollo crew did not have any life insurance.
Simon, can you play some music?
Do you have a particular playlist or a genre you want to hear?
Play my favorite music. Simon?
So this is just to give you an impression, but you see if it's about social and emotional well-being, this could help, but it could also triage maybe disease. So this will be developed in the future. And you see here for Mars, preparation for deep space missions is also going on. So if you want to see more, I urge you to go to the ibm.biz website here, and Simon will actually give you a tour around ISS. That's it's a very nice website. So the conclusion here, to cut it short, that I personally think that future deep space astronauts will be helped and coached and monitored and warned by data-driven and knowledge-driven systems that could be sensors, clothing wearables, and up to companions like Simon, and ultimately very smart robots. And that AI will be at the heart of this technology. So thanks for your attention, and I especially want to thank my colleague Matthias Biniok, who gave me a lot of material that I'm presenting today, and who was close to the development of Simon. Thank you again.
Thank you, Nikki. That sounds very promising. It makes me think of that movie, Her, in which there's an AI who's very advanced and becoming very close to people. Do you think
Yes.
one day this technology can become more sensitive than humans?
Yeah, of course it can learn, and with her, well that could be real actually, that movie, because you've heard Simon with tonality and understands what you're saying, the context, and can answer to your questions or remarks in a similar fashion, and as long as you train such a system in the proper way, I think this can be reached. But when it comes to healthcare, I think that such a system, but also what I showed, wearables or other devices, can be of help. And yeah, so we will see. But AI is everywhere. It's even in ISS now, and in the things that are put up in the air by Tesla and the other companies.
So I would like to thank you for showing me, at least, the first robot that's free flying in space.
Yeah.
And I've seen hundreds of robots, autonomous robots, in my life. So I would like to thank you for that. It's amazing.
Yeah.
It's really difficult to create these machines. But my question is not so much about the robot, but it's about the computational power, because at the moment computational power is on Earth. But if you want to go into deep space, the quantum computers, well, we might be able to install one on Phobos in like 30 years or something.
Yes.
But what do we do in the meantime with all the computing power that is required?
Yeah, that's true, because if we need today, if you want to develop a machine learning system, you need a lot of power, and we are really running into the limits of what we can do with that, because you need the top supercomputers of today to really do this, and we already did a trick with, and that probably, with the GPUs, the graphical processing units being used together with CPUs, the regular hearts of computers. But yeah, this will be a problem because we cannot build in that big machines into those. So we need to develop these systems on Earth and yeah, put them into space as a complete system, and then it needs to be updated, of course, now and then. So I hope that updates can live with a travel of 20 minutes through space to Mars, or to a vehicle that goes to Mars. But that's how it should be done, of course. And maybe if we can install in the future a quantum computer on Mars, that would certainly be something, But we also need a hospital on Mars, and we have heard a couple of speakers about building homes in Mars, but we also need hospitals and medical equipment, and we need to have a supply of medication. How do we do this? So there are many more aspects involved, but okay, we'll see.
I have maybe the last question. I've been involved in benchmarking domestic service robots for a big part of my professional life.
Okay.
And I can imagine that we require something for medical space robots, which would be like an international and global effort in order to actually get there in the next 5 to 10 years.
Yeah,
is there something going on like that?
No, not that I'm aware of. I think it's a very good idea as an international effort. But you see that each of the countries take a standard robot technique, like the Now or Pepper robot, from SoftBank, and then they develop their own application on that. That's how it's being done. So there's no effort going on whatsoever to have, maybe a genius medical robot that could help with these travels. Yeah, that's a pity maybe, but I think it's very difficult to organize that. And we need to learn still from the humanoid robots to prepare them for medical life, so to speak. I think that robots will be, like Asimov already predicted, that robots, and in the movies, of course, that robots will be part of these missions in the future. Yeah.
Yes, okay. Thank you very much, Nikki, for your presentation.
You're welcome.
I really thank you very much. So we've come to the end of our conference, Happy and Healthy Living on Mars. I would especially like to thank our excellent speakers and also our sponsor, Navarra, of course. And thank you all for joining. If you enjoyed watching it, maybe you can consider giving us a donation. It's on our website, marssociety.space. There's a button you can use. And we will use that money to organize other events for helping the Mars mission, of course. So thank you very much from me, and hope to see you again.
Yeah, thank you very much. And don't forget to like us.